Okay, this is a helpful hint on the 3D book problem number 2. Fair warning, this one's a bit of a booger. So, where are we starting off with? Well, what do we know? We know that there's a golf ball. We know that it has a flight path, which we are told gives it an x displacement of 301.5 meters. Okay, and we know that it is launched with an angle of 25 degrees to the ground. What we want to know is the maximum height. So delta y max. And you'll notice that I put in that delta y max. That's really important because we're going to deal with a couple different delta y's here. Okay, so there's not a whole lot in this problem, is there? It doesn't give you a lot of variables. Recognizing the whole situation and drawing it out is really important. Here's something else I'm going to draw your attention to. What is the delta y of the ball overall? It's 0. Interesting. And what is the Vy at top of flight? Interesting. Also 0. Okay, we're going to create an expression for this entire thing that relies on the fact that the delta y overall is 0. Trust me on this. It'll all work out. Here's the big key. You're going to need to write an expression for this as if you were going to solve it as if you had Vi. So you're going to go through and list all your variables just as you always have, and list those expressions for Vix and Viy. They haven't changed. Vi cosine theta, Vi sine theta. Ignore the pesky little fact that you don't have Vi. Remain calm. It's okay. That's the first hint, trick, tip. If that's all you need, and you can solve it from there, go ahead, fight with it for a little while. Don't watch the rest of this. If you've fought with it for a little while and you still aren't getting it, let's go to the next step together. So let's follow this logic, as I was saying. If we're talking about the overall flight, we're talking about the initial velocity. We don't know or care about final velocity. We're not going to concern ourselves with any of that. Do we have an overall delta x? Sure, 301.5 meters. Do we have an overall, and note that I am writing that in there, delta y? Yes, it's 0. Boy, is that important. Do we have an acceleration on the x? Yes, 0. Do we have an acceleration on the y? Yes, negative 9.81 meters per second squared, negative g. Do we have a way to use time as our bridge? Of course we do. So, we're going to do our standard old hat trick. Delta x equals Vix delta t plus 1/2 a sub x delta t squared. Get rid of all that. Cool. Now we can write the expression for delta t, delta x over Vix. And putting in our substitution with our expression for Vix, that gets us delta t equals delta x over Vi cosine theta. Cool. Now, do we have an equation on the y-axis that would tie together all the things we're looking at here? We do. Same one. Okay. Well, that's beautiful. But here's the thing. Is there anything on the y-axis that's 0 that allows us to cancel stuff out? Aha. Okay. Well, that's compelling. Let's take that a little bit further. I've rewritten it and put in my expression for VIY, VI sine theta delta t plus 1/2 a sub y delta t squared. Well, that all equals 0, which means I have pretty much free reign to do this. Well, what does that do for me? What am I trying to solve for? It's a great question. What am I trying to solve for? Well, actually, nothing with this. Huh? What I'm going to end up with here is an expression for VI. Huh. That could be useful, couldn't it? It could. I did this before I substituted my expression for delta t on the x-axis in, because what this allows me to do is get rid of 1 delta t. Oops, and I forgot the 2 down there on the bottom. That's a great algebraic error, isn't it? So now I have negative VI equals a delta t over 2 sine theta. Beginning to look a bit more manageable. We have a little bit of algebraic work to do to get this to a point where it's manageable. But what we've done is create an expression for VI. Okay, we're not going to solve for it. Have you figured that part out yet? We don't solve for a lot of things. We create expressions and we fight with them till the bloody end. Now, if you can go from here, here's the last clue I'm going to give you. This all relates to the overall path of travel of the ball. Okay, I'm going to shrink all of that, because you could actually list a whole nother set of variables, some of which would be the same, some of which would be different, that are called top of flight. And at top of flight, well, your Vx is the same as your Vi was, right? Because there's no acceleration on the x-axis, so it's still Vi times cosine theta. Your VIY is still going to be your initial VI on the y-axis, VI sine theta. But at top of flight, you now have a VFY, which is 0. Because we can treat this object as though it's going up and coming straight back down. Okay, pretty handy. At that delta y max, that's going to be at this point. Now, well, guess what? Do we have any equations that we could apply to just the y-axis that would incorporate VIY, VFY, delta y, and AY? Huh. Yeah. By golly, we do. It goes right back to the kinematics equations. Which one of those connects all of those things? Oh, why, it's our old friend, one we haven't seen in a while. VF squared equals VI squared plus 2a delta y. And of course this would be VFY and this would be VIY. Well, now we have some substitutions to do. I'm going to let you take it from there, using the expression that we have created, using all the expressions we've created for VIY, for delta, well, we don't need an expression for delta y. Using all of those expressions, this would be, of course, delta y max. Can you solve it? I bet you can.